So welcome back again. Okay, so if you recall, in my last class, I was doing area of your surface of revolution. Okay, I told you that like basically what we were doing, we were using some concepts from single variable calculus, and I was extending it to something happening in three-dimensional space, right? And we were working it out, and we were able to find out the area of surface of revolution. Okay, so today I'm going to go to volume of surface of revolution. But let me tell you that all these are prelude to what we are going to do eventually. Your multiple integrals. Okay, multiple integrals. So far, as you can see, we are still dealing with definite integral, which is only considered across an interval. Okay, so when we are going to consider some integral over some region in two-dimensional plan, then it is going to be not necessarily two-dimensional plan. It can be three-dimensional space also. Okay, but firstly we are going to extend it to two-dimensional plan. So from there we'll start our multiple integral. Okay, so what I'm going to do today first, like this, I am going to go to volume of surface of revolution. But before that, let us start with simply volume. Simply volume of some known shapes. So you know that if I want to find out the volume of a circular cylinder, so what I do, I simply take the area of the base, and if the area of the radius of the base is r, and if the cylinder is of height 8. So then you know that area of the base is going to be pi r square, and you simply multiply it by h, and that is going to give you the what? That is going to give you the volume. Okay, and likewise, if you have a rectangle, yeah, if you have a rectangular box like this, okay. So then if I know the breadth, length, and height, so you know that the volume is simply it is x, y, z, something like that. Okay, we have already worked it out. But these are something like known known shapes, and the shapes are beautifully shaped. Okay, so that we can work it out easily. So now what we are going to do, let us try to figure out how we are going to work out with the volume of something like some arbitrarily randomly shaped volume, randomly shaped maybe I should call solid, randomly shaped solid. Okay, so but again, like say what we are going to do, they are going to have something in common. Which we will be able to exploit in order to find out the volume. Okay, fine. So what I'm going to do, I'm going to consider, say, these two axes, x and y. Okay, so it is something like, yeah, from your side, I think it is fine. This is x, this is y. And then what I'm going to do, I'm going to consider some solid like this. Okay, fine. Now let us see what happens. So your solid is something like this. Okay, right? And you shouldn't think that whatever I have drawn here, that is that is simply something lying on the xy plane. It is not. So this is a solid. So It is something like this. It is something like this. The scenario is something like this. I mean, eraser here, you can consider that to be solid, right? And it is lying in space. In fact, it is lying in space. It is something like this. Is it okay? Fine. So now, what we are going to do? We are going to assume that this solid, I mean, lies in the interval AB, along x-axis. So then, what we are going to do? So I showed you the situation here. So then, what I am going to do? I am going to cut or intersect the solid. I mean, with a plan. With a plan, I mean px, with a plan px in such a way that, or maybe if I hold it like this, it will be easier for you. Okay. So the scenario is something like this. Okay. So now what I'm going to do, I am going to cut this solid with some plans, like with some plans like this in this direction. I'm going to cut it like this. I'm going to take slices like this. Is it okay? You have understood, right? The orientation of the plan. Okay. So the plan is going to be something like, I'm going to call it say plan is going to be something like this. Let me call this plan as Px. Okay, fine. So basically, this plan is what? This plan is obviously perpendicular to x-axis. So I'm calling it Px, and so this is going to be my x, variable x, and let us assume that at this location x, it takes out some cross-sectional area like this. It takes out some cross-sectional area like this out of that solid. And I'm going to call this cross-sectional area as A of x. I'm going to call this cross-sectional area as A of x. Okay. So now, what you do, let us consider this scenario slightly a bit differently. Okay. So what I'm going to do, I'm going to divide this interval AB into sub-intervals, into n sub-intervals, something like this, I mean xi, where your I goes from 1 to n. When I goes from 1 to n. So I'm going to get all the sub-intervals. So basically your A equal to x naught and B equal to x n. So I'm going to divide it by equal intervals, say delta x. And again, remember, I mean, those intervals doesn't necessarily have to be equal in length, but for the sake of simplicity, we can assume that. So maybe, I mean, this is going to be xi minus 1. This is going to be xi. So then, what we can do, say, suppose there is a point here lying in this interval xi minus y, xi. I'm calling it xi star. Okay. So here itself, I can consider it's something like this. Say, suppose this is my xi minus 1. This is my xi. So this is the interval, and this point is say xi star. So then, what is going to happen in this interval? I mean, if I take a slice by a plan parallel to this px, so then it is going to, I mean, take out a slice like this, isn't it? It is going to take out a slice like this. Is it okay? Slice like this. Fine. Is it okay?
Yes.
Yes. Yes. Fine. So it is going to be some slice like this. It is going to be some slice like this. Okay. So what I am going to call this area of this slice, I am going to call AXI star. And obviously, you know that this height is delta x. This height is delta x. And now let me tell you, even if these intervals are not equally spaced, so then what I can do, if the length of each of the intervals are different, so for this interval, I can simply use delta xi. I can simply use delta xi. Okay. So then, what is going to happen? The volume of this individual slice, if I call it say Vxi star, so it is simply going to be your AXI star into delta xi. Sorry, delta xi. Is it okay? For the time it is fine, right? Okay. So
Yes.
then if I have to find out the volume of this solid, say let us call this solid as S. So then the volume of the solid S, it is simply going to be this summation of all those slides. Delta xi, right? Delta xi. Okay. So now what is going to happen? What is going to happen?
But do you need a limit?
Yes.
Limit as n tends to infinity?
Yeah. So if I take limit n tends to infinity, it is going to give me the volume. Is it okay? Fine. So that is the way we are going to find it out. Okay, fine. And here we are assuming that the solid is such that I can do whatever procedure I have adopted. I can proceed like that. Okay, fine. And you may be thinking, so what about any randomly or arbitrarily shaped volume? So what we can do, even it is not shaped like the way it is, we can through some mechanism we can make it like this. Okay, we can make it like this. You will see later on that we'll be able to find out a way. Okay, so now let me just quickly browse through my slides so that so this is what I was talking about. Say these are these are some solids which are beautiful shapes, and the volume can be easily worked out. Okay, but you are not going to get that kind of situation every time. And so this is the situation that I told you. Say suppose I am considering x and y axis like this, and then what I am doing, I am considering. You can think about an arbitrarily shaped loaf of bread like this, and then this is the plan which is perpendicular to the x-axis. Okay, like this that I have already told you, and then it traces out a cross-sectional area AX from that. Okay, so then what we did, so here divide this solid into n slabs of equal width. And although it doesn't necessarily has to be equal width delta x as I have told you. So using the plans px1, px2 up to pxn to slice the solid. And again, see, it is easier if you think of slicing a loaf of bread. So if we choose sample points xi star in the interval this xi minus 1 xi as I have told you, we can approximate the ith slab si, the part of s that lies between the planks, xi minus 1 and pxi minus 1 and pxi. So see, it is going to be shaped like this. Okay, and so eventually I will have a situation like this. And if I add up the volume of all these slabs, it is going to give me the volume of this solid. Okay, and this is the way it is. So the volume of an individual part is going to be given by this, as I have told you. Okay. So if you add them up, then you get an approximation. Okay. But if you let the number of slices tend to infinity, so then this is what you get. So let S be a solid that lies between x equal to A and x equal to B. And if the cross-sectional area of S in the plane Px through x and perpendicular to the x-axis is Ax, where A, and remember, this A has to be a continuous function. A has to be a continuous function of x. So then the volume of S is simply this. Volume of S is simply this. Okay. So basically, what you have to find out, you have to just think about a slice which has area Ax, and then you have to integrate that function Ax between A and B. That's it. Okay. So let us start with a very easy example. Let's start with a very easy example. Say, suppose we have to find out the volume of a sphere of radius r. So then what we are going to do, say, suppose this is my x and this is my y axis. And then I am considering a sphere of radius r. So this is minus r, this is r. Okay, fine. And this is the origin. This is the origin. Okay. So then, as before, what we are going to do at a distance x from O, what we are going to do? We are going to consider a loaf of bread like this. Okay, loaf of bread like this. Okay, and this width of this loaf of bread, it is delta x. Okay. So then what is going to happen? What I am going to do? I am simply going to find out the volume of this individual slice of bread, and then I am simply going to add this up. Okay. So now you will see that what is this? If this is x, and then if this is the area of this slice A of x, so this is r. Suppose this length is y, right? So then you know that A of x is simply pi y squared. Is it okay? Fine.
Yes.
Because this is going to be the radius of the circle. Radius of the circle. Radius of the disk to be precise. And disk is nothing but the cross section of the plane Px. Okay. So, and this is going to be equal to pi your what? R square minus x square. Okay. So then the volume is simply going to be what? I mean, the limit for x, it is from minus r to r. Okay. So minus r to r. And then Ax is pi y squared. So this is r square minus x squared dx. And you know that this is very easy. So r square x minus r by r. So this is going to be pi r square.
It will be x cube. Cube by 3.
Sorry, this is x cube. I am full r cube everywhere. Thank you. So this is going to be 2r. This is going to be 2r cube, right? So your 2 pi r cube is everywhere. 1 minus 1 by 3. This is going to be 2 by 3. So your 4 pi r cube by 3. That's as easy as that. Okay, fine. So let us take another one. I'm going to say my next problem is going to be it is about some kind of rotation, because my aim is to find out the volume of surface of revolution. Okay. So the next exercise is find the volume of the solid obtained by your rotating the region bounded by the region bounded by your y equal to x cube, y equal to 8, x equal to 0, and it is about y-axis. About y-axis. And always remember, I mean, even though you know the formula, but still, I mean, whenever you are given a problem, particularly in multivariable calculus, you should try to visualize this scenario. That is going to make your life, I mean, much easier. Okay. So what it is telling me, volume of the solid obtained by rotating the region bounded by y equal to x cube. So y equal to x cube, I mean, it is going to be something like this. It is going to be something like this. So this is y equal to x square, x cube. So then your, suppose this is 8. Suppose this is 8. Okay. And x equal to 0. So your x equal to 0 is this. Okay. And about y-axis. So basically, what you are going to do, you are going to rotate this curve about y-axis. Okay. So then it is going to generate. Something like this. It is going to generate something like this, isn't it? Is it okay?
Yes.
Fine. So then, as before, what we have to consider? We have to consider a band. We have to consider a band like this. Okay. And then here, you will see that, I mean, if this is y and this is x, this is x. So then radius of this, I mean, cross-sectional area, which is nothing but a disk, it is going to be given by x. Is it okay? Fine. So that is why, because it is rotation about y-axis. So that is why my volume is going to be your pi x square delta y, and y goes from 0 to 8. Is it okay? Fine. And from here your x equal to 1 by 3. So eventually this is going to be 0 to 8 pi y to the power 2 by 3 dy. So you simply integrate it, whatever you get is the answer. Is it okay?
Yes.
Fine?
Yes.
Okay. So see, now this has already given you an idea about how to find out the volume of solid of revolution. It is nothing but you consider that band, okay, and whenever, I mean, it is surface of revolution, that band, that band, yeah, it is always going to, I mean, provide you with a disk, right? So you simply have to consider the area of that disk, and the remaining stuff is simple. Okay, fine. Now let me come to one more important aspect of area of volume of surface of revolution. See here I had a single graph. I had a single graph of a function of a single variable, and this was generating a solid like this. This was generating a solid like this. Okay, but under certain circumstances, the solid that is going to be generated by this rotation, it may not be like this. I'm going to take an example, and then you'll get to know what actually I am trying to get into. Okay, let me consider another exercise. Okay, so suppose I am considering a region R bounded by the curves, bounded by the line y equal to x and the curve y equal to x squared. Okay, so then what I'm doing, firstly I am rotating that region R about the x-axis. Okay, and then I'm rotating it about the line y equal to 2. Okay, then you have to find out the volume of the surface of revolution. Okay, not surface area, sorry, solid of revolution. Okay, fine. So I'll show you a better picture of this, but let me just. Okay, so this is my x-axis. So now this is the line y equal to x, and suppose this is your parabola given by okay, so this is your y equal to x squared, and this is y equal to x. So basically this is my region R. Is it okay? This is the shaded portion, this is my region R. Fine. So now what you have to do, you have to rotate this region, about x-axis. Okay, so then what it is going to generate? It is going to generate a surface like this. Sorry, definitely a surface as well as a solid like this. But this is going to be something like this, isn't it? This is. Sorry. This is going to be something like this, isn't it? This is going to be something like this. Are you getting my point? So basically, what I want to tell you is that if you consider a plane perpendicular to x-axis in order to cut this solid, then what it is going to do? It is going to generate a shape like a washer. Is it okay with everybody? Isn't it?
Yes.
It is going to generate something like this. Is it okay? Fine?
Yes.
So, right? So then what is going to happen? I mean, I'm simply going to take something like a band like this. I'm simply going to take a band like this. Okay, so this width is delta x, and then I'm going to work it out. Okay, fine. So then what is going to happen? If I consider this area, so if you look at that, so that means what is happening out here? I am considering, say, here. So this is my x. So, like if this length is your y1, and suppose this length is y2. This length is y2. So then this area of the shaded portion is going to be pi y1 squared minus pi y2 squared. Is it okay?
Yes.
Fine. And here in this particular case, so pi y1 square minus pi y2 square. So therefore, the volume, it is going to be, I mean, and again, here, because this is 1, 1, x is going to go from 0 to 1. So it is going to be your 0 to 1, and then pi y1 square minus y2 square dx. And what is the height y1? What is the height y1? It is simply x. Is it okay? And what is the height y2? It is simply x square. Is it okay? So that is why this is going to give you 0 to 1 pi. Then this is going to be x square. This is going to be x square square. Fine. And then you can easily integrate it. Is it okay? I'm just teaching you the concept. Okay. Anyway, I'm going to have it in my slides. Fine. So this is about it. So now the next thing is what is happening. Earlier, so this part is done. This part is done. So let me come to the second part. What happens if you rotate it about the line y equal to 2? So now, okay, let me read it. Okay, so and let me make it a bit smaller. I have a purpose for that. So now, so this is still my reason, but I'm making this as this is as 1, 1. So now, say this is 1, say this is 2. So what I have to do, I have to think about this. I have to think about rotating this region about this line. So then what is going to happen? This is y equal to 2. This is say 3. This is 4. So then what we are going to get? We are going to get something like this, isn't it? We are going to get something like this. We are going to get something like this, isn't it? So it is going to generate. Are you getting my point? It is going to generate something like this. Is it okay? Is it okay with everybody?
Yes.
Fine. So now you look at this. This line is your y equal to 2. So now what is going to happen? And now if you consider a slice, a slice at a distance x, your x from the origin. So then what is going to happen? I mean, it is going to be like if you consider this washer, so look carefully. So now I will have to consider this whole length to be y1 and this length to be y2. Is it okay? Isn't it?
Yes.
Fine. So now if you consider y1, just a minute. Yeah. If you consider y1, this length, y1, so y1 it is going to be 2 minus x squared, right? Just a minute. And if I consider this length, So this is going to be 2 minus x, right? This is going to be 2 minus x. Okay. So here what is going to happen? It is going to remain same, but y1 is going to be 2 minus x squared and y2 is going to be 2 minus x. So simply plug it in here, but now the thing is that again, the limit is going to remain the same for x, okay, from 0 to 1. Okay, so instead of y1 you use this, and instead of y2 you use this, and then you are going to get the desired result. Okay, so now what I'm going to do in my slide, I'm going to show you how you can generalize this kind of situation. Whenever you have a situation where the cross section by that plane perpendicular to x-axis is px, it is going to be some kind of a shape of a washer. Okay, so then what happens? So this thing we have already learned. This example we have done. So this is the situation. And again, interestingly, again, if you say use these number of subdivisions, so you will see. I mean, if you use 5 discs, then it is going to give you a volume 4.27 discs, 10 discs 4.2027, 20 discs 4.1940, and the actual value is 4.18879. So you can see as you increase the number of those slabs, so then it is converging towards the exact volume. Okay, fine. Then yeah, this is fine, and this you can easily do. This is a straightforward example. You can look back at home, and this is the example I was talking about. So you can see that the region R it generates is its area AX. It is in the shape of a washer. Okay, it is something like this, and this is the second situation. Fine, this is the second situation I have already explained to you. Okay, and this is the general situation. Okay, fine. So the solvents in the examples, all the examples that we have considered, you know, they are solids of. Not in all the examples. Except one example that we have considered, what we have done, and even like say you can consider this one. You can consider the very first example. You can consider it to be the surface of revolution of the semicircle x squared plus y squared equal to 1. Isn't it? About x-axis. It is still going to generate the sphere. Right? It is still going to generate this sphere x squared plus y squared plus z squared equal to 1. Okay. So the solids in the examples are all called solids of revolution because they are obtained by revolving a region about a line. In general, we calculate the volume of the solid of revolution by using the basic defining formula. This, see, it can be either, in terms of the function of x or in terms of the function of y, depending upon the situation. For example, if you look at the second example, when we consider, y equal to x squared, when we, revolved the curve y equal to x cubed about y-axis. So then we were doing it through this formula. Okay, and we find the cross-sectional area AX or AY in one of the following ways. If the cross-section is a disk, we find the radius of the disk and use A equal to pi into radius square. Fine. And if the cross-section is a washer, we find the inner radius R in and the outer radius R out from a sketch and compute the area of the washer by subtracting the area of the inner disk from the area of the outer disk, which results in this. So this is the situation. Fine. Okay. So this is about volume of surface of revolution. Okay, or volume of solid of revolution. So earlier we did area of surfaces of revolution. So these two concepts, although they look like, you can simply use your definite integral for a function of one variable, but eventually it gives you something which comes out in the three-dimensional space. Okay. So next thing that we are going to do, we are going to move into actual your multiple integrals. Actual multiple integrals. So how it is going to look like? So it is going to be something like this. It is going to be something like this. So here what is happening? I'm considering the function. I'm considering the function say f of xy equal to 16 minus x squared minus 2y squared. And then suppose I have told you that find the volume below the surface which lies above xy plane. So then what we are going to do? And then suppose this one is looks very difficult. So here it shows the solid whose volume is calculated in example 2. Okay, forget about it. Suppose this is the solid. This is the solid we are considering. This part we are considering, and it looks like a pretty complicated one. Like say it lies above the xy plane, below the paraboloid. This paraboloid z equal to x squared plus y squared, and between the plane, y equal to 2x. This is y equal to 2x, and again y equal to x squared. This is y equal to x squared. So it looks quite complicated, and I have to find out. So suppose this volume. So although it is looking very complicated, Say this one. So the volume of the red region. I have to find out. So basically, we are going to deal with this kind of problems. Okay, when we consider multiple integrals. Okay. So now, what I'd like to do, I'd like to take you back to a review of definite integral for a function of single variable. Okay, and then I'll come to multiple integral, obviously. Okay, see, suppose we are considering a function of one variable given by y equal to f of x in the interval a b, and of course we are assuming that it is a continuous function. So then, in order to find out the definite integral of a function f of x between the points a and b, so what we did, we just divided that interval into sub-intervals, and then what we did in each sub-intervals, we considered a rectangle, right? Whose width was the length of that interval, and height was nothing but given by what? The value of the function inside a point in that interval, right? And then we simply what we did, we took the sum of all those rectangles, and as we let the number of sub-intervals or number of these rectangles tending to infinity, we got the definite integral, right? So exactly, we are going to do double integral, okay, in the same way. Fine. So how to go about it? Okay. Fine. So what we do here, just a minute. Let me just shake off the dust from my eraser. Okay. Fine. See, what we are considering first. Please remember, initially we will start with some very simple concepts, and then we'll move to, more complicated ones. But you will see that from these simple concepts, these complicated ones can be easily tackled. Okay, fine. What I'm doing here, I am considering a function of two variables. Okay. And because I told you that I'm going to consider simplest of the cases at the beginning. So what I'm doing, I'm considering it in the rectangle. I'm considering it in the rectangle given by AB and CD. So basically, I'm considering this rectangle. So it is XY R2 such that your X lies between A and B and Y lies between C and D. Okay, fine. So then, am I correct here? No, I'm not correct. Because if this is 0, A is going to start from there, P is going to be this. Okay, and here this is going to be C, this is going to be D. And what I am doing, I am considering this rectangle or this division also. This is my R. Is it okay? Fine. And this is my Z axis. This is my Z axis. So now, if I consider a function which is continuous function of these two variable f of x1, and also what I am doing for the time being, I am making this assumption that the graph of the function, which is a surface, it always lies above your xy plane. Okay. So then, what is going to happen? What is going to happen? I mean, the graph of the function. The graph of the function. I mean, it is going to be something like this. It is going to be something like this, which is going to lie above the rectangle. Is it okay? Fine. For the timing, it is okay, right?
Yes.
Fine.
Yes.
So then, what is going to happen? What is going to happen? Now, as we did in a function of one variable. So now, what we are going to do? Let me consider this region R. In xy plane. So it is something like this. It is something like this. So this is my region R. So what I'm going to do, I am going to divide this interval in x-axis AB into n subintervals by the point, I mean, xi, your I going from, I mean, 0 to n, where, I mean, x naught is equal to a and x n equal to b, okay? And similarly, the interval CD along y-axis, let me divide it into m subintervals. So n intervals along x-axis, n intervals for n subintervals for the interval AB and n subintervals for the interval C. Okay, so then my situation is going to look something like this. Okay, so similarly for this, it is going to be something like this. Okay, so now let me concentrate on the interval xi minus 1 xi along x-axis and the interval yj minus 1 yj along y-axis. Okay, say suppose this is my xi minus 1, this point, and this point is say xi. So similarly somewhere maybe say suppose this is my yj minus 1 and suppose this is yj. So then I am basically considering this one. I am now considering this subrectangle. Okay. So now what I am going to do here in this subrectangle, I am going to consider a point which I am going to denote by xij, yij star. Xij, yij star. So just a minute. Okay, fine. So then what is going to happen? Say, suppose my subrectangle is here somewhere. Subrectangle is here somewhere. So corresponding to this, I can get a rectangular box. I can get a rectangular box whose height is given by f of xij star yij star, right? And then what is going to happen? If I multiply it by area of this subrectangle, which I am going to call delta A, which is nothing but what? Delta A, in fact, your delta A is simply, I mean, if I call this length of those subintervals as delta xi and delta yj, it is going to be given by this. Is it okay? Fine. So, like this volume of this rectangular box is going to be given by that. So, similarly, if I consider the volume of all the other subrectangle, volume of all those, I mean columns, above the other subrectangles, right? And if I take their sum, so then what I'm going to get, their sum is going to be given by, I equal to 1. Just a minute. Let me denote it by delta ij, delta I, not delta A, delta ij. So this is delta ij. So then this is going to be my sum f of xij, yij, delta ij. So as in a function of one variable, if I let limit m and n both tend to infinity, this is going to give me the volume. This is going to give me the volume, which is what? Which is above xy plane, which is below the surface given by j equal to f over xy, and bounded by what? X lying between A and B and Y lying between C and D. So basically this is going to be the volume above the rectangular region, R. Okay, fine. So let me just show you the slides, and then again I would like to come back to this limit again. See, I still haven't defined the definite integral as such. Okay. So in the slide itself, I'm going to give you the formula of definite integral. So as you can guess, say this is nothing but it is going to be the definite integral of the function f of xy. I mean in that rectangle R. So this is for function of single variable. This is what we have done. See, we consider a rectangle R in xy plane. Okay, see, it is given by AB cross CD. Okay, and then we have subdivided the rectangle into, I mean, n subintervals. What we have done m n, subrectangles, m and subrectangles in such a way that I am dividing the interval AB into n subintervals along x-axis, and CD into m subintervals along y-axis. And although in the figure they are writing it as intervals of equal length, again let me reiterate that it doesn't necessarily have to be. As in that mn tends to infinity, eventually it is going to lead you to the same result. Okay, fine. So as I have told you, I'm considering a point in that subrectangle, and like it is given by x ij star and y ij star. So then what I have done, I am considering this column. I am considering this column of height given by this. Okay, and its area of the base is simply Aij. And if you take the sum of all the columns, it is going to look like this. See, this is the scenario. If I consider each column over each subrectangle, or yeah, fine. So now this is what it is. Double integral as volume. So now the volume is going to be simply this, as we let m and n tends to infinity. So now this is nothing but the definition of the double integral of f over the rectangle R. It is simply written by, see, I have now, see, two integral signs here. Okay, double integral over R, f of xy, dA. In fact, dA, it is simply dx dy. It is given by this. And again, of course, remember, this limit, it has to exist. This limit, it has to exist. And again, let me tell you that if this limit exists, then we say that the given function is integrable over the region R. Okay, and the precise meaning of this limit here is that for every number epsilon greater than 0, there exists an integer n such that the absolute value of the difference between this definite integral and the sum is strictly less than epsilon for all integers m and n greater than n, and for any source of central points xij star, yi star. So now you know that as we increase the number of subintervals, increase the number of subintervals. So instead of an interior point in that rectangle, so what you can do, you can simply take the corner point. You can simply take the corner point xi, yj, right? So your definition 5, it reduces to definition 6. Okay, and see, now you have to remember. This is the definition of a definite integral. 6, the definition 6. Now here, I'm not roping in any idea. I'm not roping in any idea about volume. Remember, I'm not roping in any idea about the volume. But if the function given is such that it is always greater than equal to 0, then this limit is going to represent the volume f of the solid that lies above the rectangle R and below the surface j equal to f of x. So then it is going to become the volume. Okay. So now what we can do, I'll just do one example. Okay. So this is just I'll walk you through this. Say estimate the volume of the solid that lies above this square this. Okay. So here, if you consider, simply 4 subrectangles. So then the approximate value of the volume is going to be given by 34. Okay. Now if I increase the subrectangles, so then you will see that if we go on increasing m equal to 4, so it became 41.5. Now it is 44.875, 46.48675. Okay. And there, I don't know the actual value, but they are very close to the actual. So I'm simply going to do this example. So you have to evaluate this. And again, you may be thinking, oh my God, now I'll have to subdivide it into rectangles, all this stuff. So what I'm going to do? But you will see that just using some mathematical trick. It is not really mathematical trick. It is about visualizing the surface, nothing else. Okay, so let me try to work it out, and then I will end today's class. Okay, fine. So square root 1 minus x squared. Okay. Okay, so it is about evaluating this. VA, where this region R is given by R2 such that I think X lies between -1 to 1, Y lies between -2 to 2. Okay, fine. So now what they have given that this is my X. Let's suppose this is 1, this is -1, this is 1, this is -1, and this is 2, this is -2, this is -2, and suppose this is J, this is J. Okay, so now I assume the function to be J equal to 1 minus x squared, isn't it? J equal to f of xy, and f of xy is given by square root 1 minus x squared. So eventually, this is going to lead me to what? X squared plus j squared equal to 1. X squared plus j squared equal to 1. Isn't it? Right? So it represents what? A circular disk.
A circle.
Yeah, it represents a circle. Yeah. Yeah. So it is going to be this one, isn't it? Fine. And what it has told me to do, so basically what I have to do, like okay, so see, this shaded portion is my region R. Shaded portion is my region R. So basically what I have to do, I have to find out the volume of this surface lying above xy plane. I mean basically lying above this region. Is it okay? Fine.
Yes.
So now if you look at this, what is the area of this half circle? Area of this half circle is simply
Pi
1 square.
1 square.
Right?
Yes.
And then what is the area of the base? Not area of the base. No. Sorry. Area is that, and height is what? Basically, we are considering height of this half cylinder. So this is area into height. That is going to give me the volume, isn't it? So the volume is this into this is -2 to 2 into 4, isn't it? So the volume is simply given by 2 pi. Is it okay?
Yes.
Fine. Yes. So in my next class, I am going to talk about, iterative integral. But one thing you have to remember is that, see, whenever I consider a function of 2 variables in a domain D, that domain D in xy plane or R2, it is not necessarily a rectangle. You have to remember, it can be any arbitrarily shaped domain, right? So what I'm going to do in case of arbitrarily shaped domain, that is the $1 million question. But you will see that with some simple mathematical manipulation, we can easily tackle that. Okay, so probably those are going to come in my next class. I mean, it should come in my next class, and we are going to deal with that. Okay, so till next time, let me stop it here.